Hello class and welcome to Module 5. This week we're going to be looking at the Gaussian distribution, sometimes called the normal distribution, although I try to avoid that often when I'm introducing it because a lot of confusions people have about the name normal distribution, but we're going to address those. So the Gaussian distribution is a continuous distribution and it's a very important distribution. Next week we'll learn one of the reasons why it's so important, but it has to do with the fact that lots of things in the world are normally distributed, lots of random phenomena, and it's very useful in statistics for a lot of applications. We'll see why, like I said, next week. But one thing you should know, it's called a normal distribution not because it is normal in the sense of being common or being typical or being usual. It's given the word normal because of a technical mathematical reason. It goes back in history. It has to do with mathematical norms, which is a type of measurement and stuff like that. So you shouldn't be thinking, oh, okay, if something isn't normal, it's abnormal, or some distribution is common or it's very typical, so it's normal. That's not it at all. So I don't want you to get confused with that, so that's why I call it a Gaussian often, just so it isn't confusing. Also might call it a bell curve. So let's look at it. First off, there are two parameters which define the normal distribution, the Gaussian distribution. The first is the mean, and that is where is the center of it. And the second is the standard deviation. And we're going to use these two parameters like we often do with this notation with the squiggle. The capital letter N is our notation for normal distribution. And at this point, I'm going to start saying normal. So those are two parameters. Where's the mean, where's the center, and how far is the spread? Okay, here's finally a nice picture of what it looks like. It's this curve, and it looks like some other curves that we've seen. You've probably seen this before. Some of its properties. It's asymptotic, which means the curve gets close to but never actually reaches the x-axis. This means there is actually a measurable positive probability far out in the infinite reaches positive and negative ends of the spectrum. As far as you would want to go, there's still a tiny bit of probability left out there. It never actually touches the axis, so it continues forever, okay? But there is virtually no probability out beyond 3 standard deviations. Certainly beyond 4, you would be hard-pressed to find anything worthwhile. There's really very little out beyond 3 or 4 standard deviations, but there is a little bit, tiny bit. But most of what we'll learn when we see the empirical rule is really within 3 standard deviations is the vast majority of the probability, as you can see in this curve. Okay, so you've got the mean in the middle, and then plus 1, 2, and 3 standard deviations, or minus going in the other direction. Okay, so this is the picture you should have in mind. Let's take a look at a very important normal distribution, which is the standard normal distribution. If you ever have the mean set at 0 and the standard deviation set at 1, it's called the standard normal distribution. And we're going to often see the capital letter Z used rather than the capital letter X for a standard normal random variable. The reason the standard normal is so important is because essentially all normal curves can pretty much be stretched and mapped onto the standard normal curve. So when people calculate probabilities, what they really do is they map their normal distribution to a standard normal, and then they calculate the probability on the standard normal curve, and then that's their answer for the original problem. So the stretching and recentering is called standardizing. I think we're going to look at that. Standardizing data. Any data can be standardized to produce z-scores. So a z-score is telling you, it's really looking at any value on from any normal distribution. What value does it correspond to in a standard normal distribution? It is another way of thinking of it is how many standard deviations above or below the mean that value is. So for any particular value in your data set, you calculate its z-score by subtracting the mean from the data set or from the population and then dividing by the standard deviation. This produces a new value we call z, the z-score, and you've thus standardized that point of data. Here's an example that maybe will drive the idea home. First, we're looking at a histogram. Imagine we have something like, I don't know how many, 50 values that are drawn from a population. I have listed only the first 7 of them, but you can see the values are they range from between -2 and up to 12. The mean of this data set is around 5.038, etc. The sample standard deviation 2.25, etc. Okay, so this is our data. Let's say I wanted to standardize all of these values. So for each value, what I'm going to do is I'm going to first subtract the sample mean, and then after I've done that, I'm going to divide it by 2.25. So here we're looking at the data as it's transformed. The first value was transformed into the first value became -1.58833. The next one, -0.23718, and so forth and so forth. Now you can see that the histogram looks exactly the same, except the x-axis, though that all has changed. So because we've first recentered our histogram so that it's centered at 0, and then we've scaled it horizontally so that it now has a standard deviation of 1. And if you calculate the mean and the standard deviation of standardized data, that is exactly what you will get. You will get a sample mean of 0 and a sample standard deviation of 1. So that's standardizing data and getting z-scores. And like I said, each of these z-scores tells you how many standard deviations above or below the mean that particular value is. So let's just take a look at this first one, 1.464. That is below the mean. It is 1.58 standard deviations below the mean, or 1.59, I guess. I'd round it. Standard deviations below the mean, and that's what the z-score tells you. Okay, so that's standardizing data. The empirical rule is the next kind of important thing to know about the normal distribution. It is a rule of thumb that is very handy for estimating probabilities from the normal curve. The rule of thumb, the empirical rule, says that it's sometimes called the 68-95-99.7 rule. 68% of the time you're going to encounter a value that's that's within 1 standard deviation of the mean. 68% of the data, or 68% of the probability, is within 1 standard deviation of the mean. When you go out 2 standard deviations from the mean, you're now capturing 95% of the probability. And then if you go out 3 standard deviations, you're at 99.7%, which, if you recall, I said that's almost everything. There's very little out there. That's 0.3% out in the tails once you get to 3 standard deviations. Empirical rule can be handy if you have to just do a quick estimate and you don't have a calculator nearby. But nowadays everyone has their phone on them all the time, and normal probability calculators are just a couple taps away. So it can be useful for a quick estimate, but you can always get a more precise probability calculation using a probability calculator. In fact, the next video I'm going to be doing is just going to demonstrate how to find normal probability calculations using stat powers. So I'll be posting that shortly. Okay, well that's it for now, and I will see you next video.